So we have this initial value problem here, and we want to discuss the existence of its solutions on some interval t naught to infinity. Now, how do we begin to do this here? And this is important because you don't necessarily know the initial condition here, but we can still talk about the existence of the solutions on this interval t naught to infinity. So how do we do this? Well, um, there's a theorem that is called the maximum interval of existence that says if we have some domain, some domain D equals AB by Rn, and if we have that minus infinity less than or equal to A less than B is less than infinity, in other words, A and B are in the extended reals, and A is less than B, if we have that with T naught, our initial time there on this interval AB. I'll just write on D, same thing. We want to assume that F is continuous on this domain by Rn, like that. So if we have this, and if we have F is bounded on D, F is bounded on D, then when we can say that the solution exists on this whole interval right here. So that this comes from all this part. Now this this is pretty easy to show the first couple parts of this, the domain, the AB part, like we can just say okay, T naught's not infinity, and we're good to go. But the F bounded on D takes a little bit more work, and I'm going to show you how to do that using the Gronwall inequality, which is a method of bounding the solution of this below x of t, or below some value here. So let's go ahead and do that. So I'm going to state the Gronwall inequality here. This is the general form. So I'll write that in red because it's important. So the Gronwall inequality. Gronwall inequality. There's two little fun dots over the O there. So the Gronwall inequality states that if you have u of t less than or equal to alpha of t plus t naught to t beta of s u of s ds, then you can say that u of t is less than or equal to the following: alpha of t plus the integral from t naught to t of alpha of s beta of s rather, times e to the integral from t naught to t, or s to t rather, s to t of this beta of tau, some tau d tau ds, and t naught is less than or equal to t. All right, this is a lot right here. This is looks kind of scary, but we're gonna see that this really isn't that bad, and that it can be really useful in determining the existence of solutions on an interval by bounding this thing. Okay. Further, there's another thing we can even say here, and this is going to be the one we're using in this problem. If we have that, if also this alpha is non-decreasing, meaning it's either constant or increasing, then we can even simplify this further. We have u of t less than or equal to alpha of t times e. I'll write exp. So we can save a little space there. Exp, the exponential of integral from t naught to t of beta of s ds. Now, I mean, you might be asking, well, okay, that's great, but this is super complicated, like way more complicated than this thing, right? You know, how is this going to help us, like, bound this below something? Well, you can see that the there's this u of s is right here in this original equation, but it's not on the right-hand side on this one. So we've effectively eliminated it from the right-hand side, which means that it's by itself on the left-hand side, and we couldn't say anything about its boundedness before because we don't know what u of s is, but we can now because it's on the other side of the equation and it's by itself. All right, so that's the Gronwall inequality here. We're gonna use that. All right, so let's do that for this IVP right here, this initial value problem. I'm going to rewrite it so that we can see what's going on here. So we have that x prime of t equals sine of tx, x of t plus t, x of t naught equals x naught. Don't know what the initial condition is, right? All right. So we can rewrite this as an integral equation, remember? So this is from the basics of differential equations here. We can say that the solution x of t minus x naught is going to equal the integral from t naught to t of the right hand side of this part right here. So it's going to be equal to sine of s of x. I'm using s as a storage variable, right? Because we already have t's in the integral. S of x of s, ds, and I'm splitting up the integral here, and you'll see why in a second. T naught to t of just s ds right there. All right, good. So what we can do here is we add x naught to both sides and apply the triangle inequality to get an inequality here. So let's take the absolute value of this whole thing like that. And if we add x naught to both sides, we see that absolute value of x of t, if I take the individual absolute values here, by the triangle inequality, that's less than or equal to the absolute value of this right here. It's less than or equal to the absolute value of x naught plus, let's do it like this here. I'm going to flip the order here. So we'll have the integral from t naught to s, or t naught to t, sorry, of s ds. I don't need an absolute value around that because once we integrate that, that'll always be positive. And then that's added to the integral that we had above there, plus the t naught to t absolute value of sine of s of x, sine of s of x, x of s ds. And I'm splitting up this absolute value right here um, for the purpose of using this, applying this Gronwall inequality. So if you look up here, this we have all the parts now. We see we have this is u of t right here, That's u of t. I'm just going to write in all the parts there. This right here is alpha of t, right there, alpha of t. This bit right here is h, or what do we call it? Beta. We called it beta of s. This is beta right here. And then this is x of s, obviously. So that's good. We have all these parts here. So which one of these should we use then? These are both general forms of the Groundwall inequality. This one's a little bit simpler because we can say that alpha is non-decreasing. Can we say that about this one and therefore have a simpler looking inequality? Um, well, yes. Yes, actually we can, because if we integrated that, I'll do a little aside here in green. If we integrated that that integral, let's just do that real fast. It's going to be 1/2 times t squared minus t naught squared. Remember we had t is greater than t naught, right? So that's one of our conditions. So that means that this is always going to be positive right here, at the very least constant. It'll always be increasing. So we can say that this follows the second part of this Gronwall, and we can write it like the following here. I'm gonna leave it up there so I can see it. Sometimes it's a little bit difficult to remember this, but we can say then that x of t less than or equal to um, this whole thing, x naught plus, I'll just write the evaluated integral here, 1/2 t squared minus t naught squared. Um, and that's all times the, I'll write that as a better parenthesis. That's all times this following integral here from t naught to t, or actually the exponential of that, right? exp of following t naught to t of beta of s, which is just this sine thing, absolute value of sine of s of x ds. And we've basically done it here. We've applied this Gronwall inequality very effectively here. Um, I didn't actually say this either, but in order to do this, we need to make sure that that everything is continuous. The h or the beta especially needs to be continuous on this interval. So beta is continuous on the interval t naught to infinity. Yeah. So we can apply this Gronwall inequality here. And notice that this means that this is going to be bounded on this interval t naught to infinity from what we've said before. So thus we have that x of t is bounded on the interval t naught to infinity. That's our domain from this part right here, the maximal interval of existence theorem right here. So we've just shown this part, the bounded on D part. So x of t is bounded on that. Thus, the solution on the solution of this IBP exists on the interval t naught to infinity.